So on our formula sheet, we would have, amongst others, we would have Tn equals A plus N minus 1D, and we would have Tn equals AR to the N minus 1, and then we would have Sn equals 2A plus, what's wrong? Sorry guys, I've got such a headache today and my brain is not N over 2. Sorry, I knew there was something I'd left off. N
Long
over
as we
2.
can, yeah.
Sorry, N over 2, silly me, equals N over 2 into 2A plus N minus 1D, and then here we've got Sn equals A into R to the N minus 1 over R minus 1. Okay, so those are the formulae that we would need for this particular section. So this first formula, if I call this one formula number 1, what does formula number 1 allow us to calculate? What does formula number 1 allow us to calculate? The general term for a arithmetic pattern. Term number 2 is the term formula for a geometric. Okay, so this is an arithmetic term. This is a geometric term. Okay, this is an arithmetic sum. This is a geometric sum formula. Okay, and we're going to need one of those later on. All right, so they've given us a series. So 2 plus 9 plus 16 to 251 terms. We don't know what any of the terms are beyond the 16, although we could work that out. They want us to write down the fourth term of the series. So what is the fourth term of the series going to be? It's arithmetic. So that means we have a constant difference. What is our difference in this case? It's 7. Good, Mbelenhle, quite right. So in order to work out what, yes, Keithlin, perfect. So our difference is 7. We know that A is equal to 2. That's our first term. We know that our difference is 7. So we want to work out term 4. That would be A plus N minus 1D, or easy enough, we can just say 16 plus 7, and it would end up being 23. Okay, so you've worked out the nth term already. That's fine. Okay, but we didn't need the nth term to be able to do this. Okay, that's it. Quite right, Mosey. Perfect. Now they want us to calculate the 251st term of the series. So that's the last term of the series. How are we going to do that? Outside of 3 marks, how would we calculate? And some of you have provided information that's we can use. How would we calculate the 251st term, which also happens to be the last term in this pattern? We have to find our Tn and we have to substitute 251 into that. Okay, so if we want to discover what our nth term is, we would say that Tn equals A plus N minus 1D. So our first term, A, is 2 plus N minus 1, and we know that our difference is 7. always put your difference in brackets, especially when it is negative. What ends up happening is that if you don't put the d in brackets, you forget to multiply it into the n minus 1. Okay, and it ends up being subtracted from the other terms instead of multiplied by n minus 1. You have to simplify this if you want all the marks. So this gives us 2 plus 7n minus 7. So that's why we end up with 7n minus 5. And who was it now that said that to us? It was iPhone, whoever iPhone is. All right, and now to calculate the 251st term of the series, we're going to take 251 and make it equal to 7n minus 5. Okay, so that means that 7n would be equal to 256. And if we take 256 and divide that by 7, ooh, I must have made a mistake. That's not working. What have I done wrong, guys? What have I done wrong here? Oh, sorry, 200. That I see my mistake now. Okay, all right. Sorry. It's the 251st term. Sorry, it's sorry. Sorry.
That's fine.
Yes,
It's fine.
n
We're still
equals
following. We're still
251.
managing.
Quite right. Okay,
Yeah.
so therefore, term 251 is 7 times 251 minus 5. I'm getting 1752. Okay, everybody happy with that? So 1 mark for that. Answer correct, subbing in. Okay, now the next thing that they want us to do is express the series in sigma notation. So they actually want us to write the sigma notation for this particular series. All right, so let's go back and refresh our memories quickly on what sigma notation is, first of all, and what it means. So when we write sigma notation, we have to have the sigma symbol. Then there's going to be a number that goes at the bottom and a number that goes at the top. What does the number at the bottom have to represent? So there's a number at the bottom. What does the number at the bottom represent in sigma notation? Can you guys remember? So I'm going to put a block there. What is the number at the bottom? Avio, go for it. You're welcome to unmute and speak, Avio. Unmute yourself. Okay, so Trish says the value the pattern starts with. Avio says the first value, where we're going to start. You're all on the right track. Okay, so this is where we begin subbing in. Okay, so where we begin subbing in. So the first number that's going to be subbed in. Yes. The number at the top, what does that represent?
The number of terms in the sequence.
Not always. Not always. Not always the number of terms of the sequence. Under which conditions is it going to be the number of terms in the sequence?
Maybe in the condition where I think it's, where is that? I think it's when I'm not sure. Maybe I'm mistaken. But
No, it's okay. That's okay. If you have a
I feel like
look
I'm
on,
mistaken because it's my first one. Okay, I feel like it's when, because our teacher told us that the top number does not always represent the number of terms
correct.
that start with that the sequence starts with, but
Mm-hmm.
rather, I feel like it's the number at which, after you start with your first term, you must have those numbers to complete your sequence.
Okay. All right. So the number at the top, you're almost right. The number at the top is actually the last number that's going to be subbed into the pattern. Okay, so the reason why it doesn't represent the number of terms in the pattern is because you don't necessarily need to start subbing in at 1. So, for example, I could have sigma notation like this. Let's say over here I've got n equals 3, and the last number to be subbed in as is 7. That's it. That's it. Okay, so I can't say that there are 7 terms in the pattern. So if my pattern is something silly like 2n plus 1, if I start subbing in at 3 and I end at 7, I'm not going to have 7 terms in the pattern. And that's where that rule comes from. So the number of terms in the pattern is the number at the top minus the number at the bottom plus 1. Okay, so in this particular case, there would be 5 terms. This little example that I'm doing over here, there would be 5 terms. Okay, so Trish, you're right. Okay, if you begin subbing in where n is equal to 1, then yes, the number at the top is going to represent the number of terms in the pattern, because the number at the top minus 1, the number at the bottom, plus 1 will give you the number at the top. Okay. All right. So never ever fall into the trap of thinking that the number at the top is the number of terms at the pattern. It depends where we start subbing in. Okay. So because we are writing sigma notation, we have to start by subbing in 1. All right. So the number at the top in this particular case, we know that there are 251 terms in this pattern. So we will put 251 at the top. And then what we need in brackets next to the sigma symbol is the nth term of the pattern. Okay, the nth term of the series. So we know that it is 7n minus 5. Okay, so here there would be a mark on having n equals 1 and the 251, and then putting your sigma symbol with the brackets containing your rule next to it. Okay, cool beans. Everybody good with that? Hope so. Yes, okay. And now they want us to calculate the sum of the series. So we're going to use our arithmetic sum formula. So that's n over 2 into 2a plus n minus 1d. So we know that the number of terms in this particular series, there are 251. We know that a was equal to 2. N minus 1, so that would be 251 minus 1, and D is equal to 7. And then we can work out the sum of the terms in this series. So let's just do that quickly. You guys can do it as well. And we can double check our answers. Okay, what are you guys getting as an answer? Yeah, me too, Mbalentle. All right, I'm also getting 220,127. Yes, Mosey, me too, as my answer. Okay, so calculating the sum of the series, it's simply a matter of subbing in and writing down your answer. You don't have to write the formula like I did over here. You can start over there where you just go ahead and go and sub in. I just wanted you to be clear on what it was that I was doing. Okay, so now we've done all the easy questions. Now we're going to do something that requires a little bit more effort. They want us to determine how many terms in the series are divisible by 4. How many terms in the series are divisible by 4? Where do you think we should start with this? How many terms in the series will be divisible by 4? What do you think we should do first of all? Anyone got any idea? Shame you guys were quiet last week and you're quiet again. Well, not too quiet this week, but all right, well, I'll tell you what. Why don't you write down some of the terms in this pattern? Okay, so you know that the first term is 2. Is 2 divisible by 4? No. Okay, the second term is 9. Is 9 divisible by 4? No. All right, then the third term is 16. Is 16 divisible by 4? Yes, it is. Okay, so we've identified that the third term is going to be divisible by 4, isn't it? All right. So I'll tell you what, let's just do a few more and then we can do a few at the end. So we all worked out in the very beginning that the fourth term would be 23, right? What would be the fifth term? Okay, so this would be 30. All right. Then the next term would be 37, it would. And then the next term would be, I don't want to go too far, 44. Okay, so we can see here, good, well done. So is 23 divisible by 4? No. Is 30 divisible by 4? No. Is 37 divisible by 4? Is 44 divisible? It certainly is. Right, but there's no pattern in between these numbers. All right, so let's just have a look. Then we're going to add a whole bunch of other unknown numbers together. The last number in the pattern was what? We know what the 251st term was. We know that it's 1,752. Is 1,752, is it divisible by 4? It is. Indeed. Okay, so this is also divisible by 4. Right. I think what I'd like to do is just in here, because it'll just be more obvious to you in terms of how we're going to calculate this. Okay. And then I'll explain to you exactly where we want to go. So what I'm going to do is let's just extend this just a little bit further. We know down here we've got plus 1752, and we know that it is the last term in the pattern, and we know that it is divisible by 4. All right, so the next term would end up being 51, and then we would have to add 7 again. We'd get 58, and then we'd have to add 7 again, and we'd get 65, and then we'd have to add 7 again, and we got 72. Okay, now I'm doing this on purpose just to try and help build up a pattern of the numbers that are divisible by 4. Okay, so when they ask you a question about how many terms in the series are divisible by 4, what we would need to do first of all is work out the pattern of numbers that are going to be divisible by 4. All right, so in this case, we have a pattern emerging out of our pattern. So the pattern that we're now seeing is we've got the number 16, then we've got the number 44, then we've got the number 72, and then a whole bunch of numbers that we don't know, and it ends with 1752, like so. Okay. Can we develop an nth term to describe what we are seeing in our new pattern? Okay. So our difference is 28. All right. So in this case here, in our new pattern, we've got our A is equal to 16. We've got our D is equal to 28. All right. And we know that the last term or the nth term in the pattern is 1752. Do we know how many terms make up this new series? Do we know how many terms make up this series? No, we don't. Okay, we don't know that. So we don't know what n is. Right. Can we work out the nth term for this particular pattern? All right. Okay, so we could work out what the nth term for this pattern would be. We would say Tn equals A plus n minus 1 D. All right. So now our nth term in this case is 1752. We know that the first term is going to be 16, and we don't know how many terms there are, and we know that there is a difference of 28. So we get 1752 is equal to 16 plus 28n minus 28. So now I'm going to leave our 28n on this side, and on the other side, we're going to say 1752 . There we go. Good. Well done. Okay, so that means that in our new pattern of numbers, okay, which we've worked out the first 3 terms of that pattern would be 16, 44, 72, the last term being 1752. We could then use our nth term formula, our Tn formula, and calculate how many terms there would be in this particular pattern of numbers that are all divisible by 4. So there would be 63 numbers. Okay, so how many terms in the series are divisible by 4? There are 63 of them. Okay, does that make sense to everybody? Are we okay with that? Cool. Good. I'm so glad. All right. So I know it was a little bit cumbersome to extend this pattern like I did in the beginning. But the reason I did that is because I wanted you to see the pattern of numbers. That A would be 16 now. Your next term, your second term would be 44. Your third term would be 72, etc., etc. Good question. Where would the marks be? And then Katlego, I'll take your question. All right, so it was out of 4. So there has to be, obviously there has to be a mark on the answer. I'm working backwards. There would have to be a mark for subbing in. Then there would be, just, guys, just give me one. Sorry. People knocking at the door when they know that I'm busy. Sorry, guys. Sorry about that. Okay. Then, so mark on the answer, mark on subbing in. I think a mark for getting that pattern. Where would the other mark be? Maybe rather a mark on the A and a mark on the D over there, I think. Okay, yes, Katleho, go for it. Sorry,
Hi,
you've been
ma'am.
waiting.
Hi, everyone.
Hi, Katleho. Sorry about that.
Ma'am, it's okay. Ma'am, I just wanted to know, how do you find the second pattern without doing all that, or is that the only way to find the second pattern?
I think so. I think so. I'm just trying to think if there's another way that you could possibly answer this question, another method that you could use. Because you see, I mean, theoretically, we didn't need the 72. All we needed was the 16 and the 44. And then from that, we could have established that A was equal to 16 and D was equal to 28, because that's really all we needed to establish. So I think perhaps here, I kind of wasted our time a little bit by doing that. It didn't really help us. I just wanted you to see what was emerging from this. So I would say, yes, once you'd got the first 2 terms, that's really all you needed, because you need the A, and then you can use the second term to work out, the second term and the first term to work out what the difference is. Does that make sense?
Yes, ma'am. But what if the second pattern is not at the, what's that? It's not linear. What if it's quadratic? How do you know if it's going to be quadratic or?
It can't be. It can't be, because you see, the thing is that we were talking about an arithmetic series to start off with. Okay, so you're not gonna suddenly now find in 2.5 that it's changed from being an arithmetic series into a quadratic one. Okay, so the quadratic question, what you'll find, Katlego, it will be a separate question from a question about an arithmetic series. All right, generally that's the way they do things. Where the two are connected is because your first differences in a quadratic pattern are linear or arithmetic. Okay, so that's where you sort of have a bit of overlap. But if they want to ask you a question on quadratic number patterns, it will normally be a separate question. They're not just going to suddenly say, oh, it's now quadratic. There would be too much information missing for them to do that. Okay. All right. Now, speaking about quadratic patterns, no problem. Okay, so Avi, if you divide Avio, just hold on sorry guys, Avi's just asked me a question here. No, Avio, they wouldn't be okay with that because remember, you can't have an answer for n that isn't natural. So you're onto something, but that wouldn't be an acceptable way of doing it. No, they would want you to do this algebraically, like I've set it out over here. Okay. Okay. I don't know if you guys want to do, the questions on these quadratic patterns are really straightforward. Do you want to do a little bit of revision of quadratic patterns, or can we move on to something a little bit more difficult? How do you feel? Move on. All right, cool. Not a problem. Let's move on. Okay. I wonder if that's also, let's have a look at these questions over here. We can always come back to the other ones later on if we want to. Okay, so I've included these because they are a little bit more difficult. So this might be a bit more interesting for you, something that we can sink our teeth into, so to speak. All right, so in question 3.2 here, it says if t is a real number, show that the following sequence cannot be geometric. So this is something a little bit different. So they've said if t is a real number, show that the following sequence cannot be geometric. What do you think we should do here? Where would you guys start? Okay, so try to find R. Okay, so R in terms of T. Prove that there's no common ratio. Can't we find the value of T first? Okay, so you guys are all onto something. How would you set that out though? What would you write on the page? So if you wanted to establish your ratio, your R in terms of T, how would you do that? So your ratio R is calculated how? How do we calculate a ratio? That's it. Good. Well done, iPhone. Sorry, I keep calling you iPhone. Please tell us your name so I don't keep calling you iPhone all the time. But you're quite right. So it's term 3 divided by term 2, which is the same as term 2 divided by term 1. Right? So if we use this structure for R and sub into that, term 3 is -1. Term 2 is -1 minus t. Then is equal to term 2, which is -1 minus t, over term 1, which is 3 minus t. Okay. Now we would need to cross multiply. Okay, so we're going to take -1 into 3 minus t is equal to -1 minus t multiplied by itself. Okay, so this gives us -3 plus t is equal to -1 times -1 is 1. Then it would be plus t, so that would be 2t plus t squared. Okay, so it's quadratic. So we would end up with t squared. Then here it would be plus t. And then here, okay. Now what would you do? Can we solve this? Okay, so Trish, if we did use the quadratic formula, what would end up happening if we tried to solve for t now? Okay, so if we said t equals -1 plus or minus, and then here we ended up with 1 squared minus 4 times 1 times 4 over 2 times 1. What's going to end up happening when we put that onto our calculators? Exactly, right? There would be no solution, no real solution. Math error, precisely. So really what they want us to do here, I suppose we could set it out like this. But what they're actually really looking for here is a link to nature of roots. So in other words, what we can do is, instead of actually trying to use the quadratic formula, which is not going to work, is let's work out the value of delta, because that tells us about the nature of the root, doesn't it? Okay, so here we would say delta is equal to, then b would be equal to 1, 4, a is also equal to 1, and in this case, c is equal to 4. So we would end up with 1 minus 16, which would give us -15. Okay, so therefore, delta is smaller than 0. Okay, and because they told us that t has to be a real number, if delta is smaller than 15, what it means is that inside our root over here, we have got a negative number. Okay, which we can't have because they told us that t is real. So that means that our sequence cannot be geometric. Okay, so because delta was negative, therefore the sequence cannot be geometric. Okay, does that make sense to everybody? Cool. All right. Okay, so that was something that was a little bit different. So the sequence cannot be geometric because delta is equal to 0. right? Or b squared minus 4ac is smaller than 0. Okay, let's have a look at the next question. So question number 4. Here they tell us that a series, a plus ar squared plus whatever, has a sum to infinity equal to 1. Okay, what's the formula for sum to infinity? So sum to infinity is equal to a over 1 minus r. So if they tell us that this particular series has a sum to infinity, that's it, of 1, we know that 1 is equal to a over 1 minus r. Okay. A second series whose terms are the squares of the above series has a sum to infinity equal to 5 over 6. So now we've got a second series where the sum to infinity is equal to 5 over 6. But they've told us that the second series terms are squares of the above series. So how would I write the first, second, and third terms of the second series? If they were squares of the first one, how would I write that second series?
Ma'am, would square each and every term of the first sequence.
Exactly. Beautiful. Well done. So in other words, the second term, the second series would be a squared because we're squaring your a. Then we would end up with a squared r squared as our second term. And then as our third term, we'd end up with a squared r to the power of 4 plus whatever. Okay. Under these conditions here, our a value is now a squared. Can you see that our first term is now a squared? So that means that over here, we'd have a squared. Now we need 1 minus r. So remember, r is calculated by taking term 3 and dividing it by term 2, or taking term 2 and dividing it by term 1. So if we have a squared r squared and we divide that by a squared, r is now equal to r squared. So this is going to be r squared like so. Does that make sense to everybody? Everybody happy with that? Yes, 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 yes. Okay. All right. So we've made 2 equations. We've made this equation, your everything squared of IO. Okay, so you would take that and you'd square it. You'd take that and you'd square it. You take that and you'd square it. Okay, so I think I did do that correctly. I'm just checking myself again. Yes, that is right. What I have here in orange. Okay, so now what we have, sorry, this is question 4. No problem of IO. So now what we have, let's just scooch over just a little bit, are 2 equations. Here is equation number 1, and here is equation number 2. So they wanted us to determine the common ratio, or R, of the first series. Exactly, Mbalendle, quite right. Should I let you guys try this by yourselves? And then let's see what answers you come up with, instead of me just doing it for you. We've made the equations together. Let's see what values you come up with. Yolanda and I will be quiet for a few minutes and give you guys a chance. Okay, cool. Yeah, sure. No problem, Mbalente. Off you go. Well done, Trish. Good job. First answer that came in. That's what I got too. Good. Nice. Well done. Let's see what some of the others are saying. Mbalendle, you're on the right track, but there's just a little something that's missing. Remember, you are working with a sum to infinity. So when you calculate the value of r, there's a restriction on r. Okay, r has to be greater than -1, but smaller than 1. So I think you've just left something off. Just have a quick look. You're very close. Okay, so I'm going to start. Oh, okay, iPhone, it's all right. I'm going to go through the solution with you now. Right, well done for trying. Okay, something's obviously just gone a little bit wrong with your numbers. Okay, but no stress. What I'm going to do is I want to make A the subject of the formula so that I can sub in over here and I can work only with my R's. Remember, I'm going to sub in, I'm going to rearrange my linear and always sub into my quadratic. So when I cross multiply over here, I get A is equal to 1 minus R. And now I'm going to take that and I'm going to sub it in over here. So I've got 5 over 6 is equal to 1 minus R, and I'm going to square that, and that's over 1 minus R squared. Now what I can do, again, is cross multiply. So you've got 5 into 1 minus R squared is equal to 6 into 1 minus R squared, like so. So removing your brackets on the left, we'd have 5 minus 5r squared. And here we've got to square our binomial before we can times by 6. So when we square our binomial, we would have 1 minus 2r plus r squared. Taking away our brackets, we'd get 6 minus 12r plus 6r squared. Okay, so Mosey, your answer was similar to what iPhone sent me. Something's gone a little bit wrong. So just check you're working against what I've got here. And let's see if we can find your mistake. So now it's quadratic. So I'm going to add 5r squared to both sides. That would give me 11r squared. I'm going to bring down my minus 12r. And then I'm going to take 5 away from both sides. So I'd end up with plus 1 over here. Have you seen your mistake? Okay. Good. Hopefully, Mosey can see their mistake too. All right. And now, again, you can use the quadratic formula if you want to. You don't have to factorize here if you don't like factorizing. So you'd end up with r is equal to, okay, so negative 12 plus or minus b squared minus 4ac all over 2a. Okay, and 2 solutions for r. You've seen your mistake. Okay. All right. So otherwise, you could factorize if you wanted to. Those of you that did factorize, you would have had 11r in one bracket one R in the other bracket. Because there's a minus in the middle, both brackets have to be a negative, and then we'd have 1 and 1 like that. Okay, so either R would be equal to 1 over 11, or R would be equal to 1. Okay, but we're dealing with sum to infinity. Okay, so there's a restriction on the value of R. Okay, R is not allowed to be equal to 1 over here. Okay, so we would have, that's not equal. Remember, R has to be greater than -1, but smaller than 1. Okay, so this is our only solution. R would be equal to 1 over 11. Okay, so now, Katleho, I see you've got little crying faces. iPhone, you've got some crying faces. Have you been able to figure out where you went wrong?
Well, for me, ma'am, I just multiplied the whole thing with 5 over 6. And for some reason, I forgot that to remove the denominator, I can multiply 6 on the other side. So I've been stuck there. I feel so sad.
Oh,
But thank you.
shame. That's okay. As long
Right.
as you figured, that's okay. As long as you figured out what you've done wrong, that's fine. Okay. All right.